Okay, in this video we're going to start section 2.6, and that's going to deal with combinations of functions and composite functions. And this will be spread out over two videos. Here's the objectives we're going to cover through those two videos, and I think we'll get through the first three in this one here. Find the domain of a function, combine function using using the algebra of functions, specifying the domains, and then we'll form composite functions. Actually, no, the divider line should be one up. We'll get to the composite functions in the next video. So, if a function f does not model data or verbal conditions, its domain is the largest set of real numbers for which the value of f of x is a real number. Exclude from a function's domain real numbers that cause division by zero and real numbers that result in an even root, such as a square root of a negative number. Okay, when you're considering the domain of a function, there's two things you want to remember. Never divide by 0. One, do not divide by 0. And two, uh, no negatives under even radicals. So if this is an even index, like a square root or a fourth root or a sixth root, we don't want to have any numbers that will result in a negative underneath that radical. So let's see here. In example 1, find the domain of this function. So you got to ask yourself, is there any chance of dividing by 0? Well, in this problem, no, there's no division at all. Are there any even indexed radicals, square roots or fourth roots or such? And again, the answer to that question would be no. So our domain here would be all real numbers. Or you can write it like this, I guess, negative infinity to positive infinity with our interval notation. Again, with this type of function, there's no number that we cannot plug in there. Again, we're only worried about dividing by 0 or negatives under even radicals. Okay, let's see here. Second one, I see no radicals anywhere at all in the problem, so we don't have to worry about negatives under even radicals. But we do have a fraction, a ratio, and we're worried about dividing by 0. So to find the domain of this function, I'm going to take just my denominator, x squared minus 2x minus 3, and set it not equal to 0, because that's what I don't want to ever have happen. I don't want this to equal 0. And we can solve this just like we solved for 0. We're going to factor. X minus 3 and x plus 1 will be the two factors. And in the past, we would set each of those factors separately equal to 0. Now we're going to set them each separately not equal to 0. So if x minus 3 does not equal 0, that means x cannot equal positive 3. And if x plus 1 cannot equal 0, then x cannot equal negative 1. So there's our two numbers that must be excluded from the domain. We can't have a 3, and we cannot have a negative 1. I guess with a set builder notation, you could rewrite that as x, the set of all x such that x does not equal negative 1 or 3. Or if you prefer interval notation, our first interval would be from negative infinity to negative 1. And we would union that with the set from negative 1 to 3. And we would union that with the set of 3 to infinity. Okay, so there's the domain for letter B. Letter C. Is there any chance in letter C to divide by 0? No, there's no division at all. But I do see everything here is under a great big radical, and it is a square root. So we're worried about negatives appearing under even indexed radicals. So what I can do is just take what is under the radical, just the 3x plus 12, and say that what is under that radical must be positive. It must be greater than or equal to 0. And we're just going to solve for x. Subtract 12 from each side. 3x is greater than or equal to negative 12. Divide through by a 3. X must be greater than or equal to a negative 4. If we plug in any number less than a negative 4, we'll get a negative underneath the radical. Like just for argument's sake, let's say negative 5. Negative 5 is less than negative 4. If I plug in a negative 5, that'll become a negative 15. Plus 12 leaves a negative under the radical. So our domain here is x must be greater than or equal to -4, or you set builder the set of all x such that x is greater than or equal to -4, or interval notation, bracket -4 comma infinity would also work. Okay, in the last case here, letter D is the most extreme of them all. We do have division, so we're worried about our denominator equaling 0. And we also have a radical, which is also in our denominator, which we always want to be greater than or equal to 0. And since now here in letter D, our denominator is our radical, we are going to take our denominator, just more specifically what is under our radical in the denominator, and we're going to set it greater than 0. Notice we're not going to set it greater than or equal to, because the or equal to would give us a chance to zero out the entire denominator. So 1, we want our denominator to not equal 0, so I don't have this or equal to. And 2, we want what is under that radical to be positive, greater than 0. So let's solve this for x. I'm going to subtract 14 from each side. And then I'm going to divide by a -2, remembering to flip my inequality when I divide by a negative. So here my domain is x must be less than 7. Anything greater than 7 or exactly equal to 7 leads to bad things, either a 0 in our denominator or a negative underneath the radical. So let's see here, I guess for set builder notation, set of all x such that x is less than 7. Or you could do interval notation, -infinity, comma 7. And then it would close that with a parenthesis. And there we go. Let's see here. It looks like we have a great question. When finding the domain of a function, when do I have to factor? In parts A and B of what we just did, observe when to factor and when not to factor a polynomial. In the first one, did we factor this and set each factor equal to 0? No, it says do not factor x squared minus 7x and set it equal to 0. No values of x need to be excluded from the domain. Again, in letter A here, there was no chance to divide by 0 because there was no division at all. In letter B, we do have a ratio, a fraction, so there is a chance to divide by 0. So it says here, do factor x squared minus 2x minus 3 and set it equal to 0. We must exclude the values of x that cause this denominator to 0 out. Okay, now we can do some algebra stuff here with functions also. We can add them, subtract them, multiply them, and divide them. Sum, difference, product, and the quotient of two different functions. So here we're going to let f be a function and let g be some other function. We can add them, f plus g of x. We can subtract them, f minus g of x. We can multiply f times g of x. Or we can set them up as a quotient, f divided by g of x. These are all functions whose domains are the set of all real numbers common to the domains of f and g, well, or more specifically, where they intersect. And we define them as follows. F plus g of x is simply take the functions and add them. F of x plus g of x. F minus g of x, the difference of the functions, is just f of x minus g of x. Product, f times g of x is f of x times g of x. And the quotient, f divided by g of x, is f of x divided by g of x, provided we figure out where g of x does not equal 0. So let's see here in example 2, we're going to do one of each, add, subtract, multiply, and divide. And it says also determine the domain of each function. Well, first let's determine the domain before we even look at composing them or adding and subtracting them. F of x here, its domain would be all real numbers. There's no division by 0, there is no radicals. Same thing for g of x, x squared plus x minus 2. It's a simple polynomial. There is no division. There are no radicals at all. So this would also be all real numbers. So both of our functions, f and g, both have a domain of all real numbers. So for letter A, f plus g of x is just f of x plus g of x. We're just going to take the two functions and add them together. If we can, we combine like terms. So f of x is 2x minus 1 plus g of x is x squared plus x minus 2. So let's combine like terms. My highest power is x squared. That'll go first. And then I have a 2x plus an x. That's plus 3x's. And then a minus 1 and another minus 2 is minus 3. There is our function f plus g of x. The domain of this would also be all real numbers. It's a simple polynomial. There's no division. There's no radicals. So we can plug in any value of x that we want. Letter B. F minus g of x. And that's just f of x minus g of x. If you are going to make a mistake, it's probably going to be here. When we subtract g of x, we have to remember to subtract it as a quantity. So f of x goes first, 2x minus 1. And now I'm going to subtract g of x, and again subtract it as a quantity. So g of x will have to be parenthesized off. X squared plus x minus 2. Very easy to forget the parentheses and just put the negative on the x squared and forget about the rest of the g of x function. So before we can simplify, we're going to have to distribute that negative. So we have our 2x minus 1, and now it's a minus x squared minus x plus 2. When we distribute negative, negative becomes a positive. So let's combine all like terms. We'll put our negative x squared first, and then we have a 2x minus x, which will be plus 1x. And a negative 1 plus 2 takes us to plus 1. So that is f minus g of x. Again, don't forget to distribute the second function as a quantity. All right, letter C, multiply. F times g of x. And remember, that is just f of x times g of x. We're just going to take the two functions as given and multiply them. So here's f of x, 2x minus 1. And then g of x is x squared plus x minus 2. All right, let's multiply. 2x times x squared is 2x cubed. 2x times x is plus 2x squared. And then 2x times minus 2 is minus 4x. And distribute the negative 1. Negative 1 to x squared is minus 1x squared. Minus 1 to x is minus 1x. And minus 1 to minus 2 is plus 2. So now we can collect up all our like terms, and this will be our final combined function, f times g of x. So we have our 2x cubed, plus 2 minus 1 is plus 1x squared, and then we have minus 5x's and a plus 2. Ooh, and I think I forgot, for part B, when we subtracted, the domain of that function would have been all real numbers again, from negative infinity to positive infinity. Again, our original functions, f of x and g of x, both have the domain all real numbers, so their sum and difference will also have that same domain. Here's our f times g of x function, 2x cubed plus x squared minus 5x plus 2. Its domain is also going to be all real numbers, from negative infinity to positive infinity. Again, because there is no division by 0 and there is no even indexed radicals. All right, last one, letter D, f divided by g of x. F divided by g of x is as simple as f of x divided by g of x. Remember, but g of x cannot equal 0. We don't want to divide by 0. So the f of x function goes up top, 2x minus 1. G of x function goes in our denominator, x squared plus x minus 2. So that is our f divided by g of x and the domain. Remember, we do not want this denominator to equal 0. So x squared plus x minus 2 cannot equal 0. Let's factor. X plus 2x minus 1 is our factorization, and those factors cannot equal 0. So x cannot equal, this will turn into a negative 2. And x minus 1, add 1 to both sides, that'll be a positive 1. So there's our domain. X cannot equal those two naughty numbers because either one of those numbers would zero out our denominator. Okay, and example 3 is our last example for this video. Adding functions and determining the domain. Okay, now here's two separate functions. F of x is a radical, square root of x plus 3. And g of x is also another radical, square root of x minus 2. So they want us to find each of the following. First is the easy part, f plus g of x. F plus g of x. And that's just f of x plus g of x. So I take my f of x function, radical x plus 3, and I add to that my g of x function, radical x minus 2. And now for part B, they want the domain of that function. So first, let's look at the domain of the individuals. F of x was radical x plus 3. So that means x plus 3, what is under the radical, we want that to be greater than or equal to 0. And if I subtract 3 from each side, x must be greater than or equal to negative 3. And then for the other function, g of x, it has its own domain. G of x was radical x minus 2. So I want to set what's under that radical greater than or equal to 0. And add 2 to both sides. X must be greater than or equal to positive 2. Now the domain for the sum function, f plus g of x, is the intersection of these two graphs. So what points do these individual domains have in common? Or let's think about it even, you could think about this graphically. For g of x, we want to be greater than or equal to positive 2. So if here's positive 2 and I'm headed off toward infinity, there's my domain for g of x. Now what about f of x? Well, f of x's domain is greater than or equal to negative 3. So I'll put that over here, negative 3, and we're off this way. Remember, the domain of the combined function, f plus g of x, is the intersection of these two. Or I could think about it as the more restrictive. You know, could we plug negative 2 or negative 1 into the summed function? No, because those would not work in the second piece of it here, that g of x function. So our domain here, again, if you look at the graph, where would these graphs overlap? Let me extend this red arrow out farther. Well, from negative 3, negative 2, negative 1, 0, 1, and 2, we just have a domain of f of x, but not g of x. As soon as we get to positive 2, there we have our overlap, our intersection of those two domains. So here our domain is going to be from 2 and up, 2 to infinity. All right, some practice problems for you. Pause the video and then try them out and then fire it back up and see if you got them right. Okay, for the first one, it just says find the domain of each. So for letter A, I see it's a simple polynomial, no division, no radicals, so it's all real numbers, negative to positive infinity. Letter B, no radicals, but we do have a fraction. We do not want our denominator to equal 0, so that x squared minus 49 cannot equal 0. Okay, we could either factor this side into x plus 7 times x minus 7 and then set each factor to 0. Or I could just add the 49 to each side and say x squared cannot equal 49. And when we square root each side, x cannot equal plus or minus 7. So there's our domain. Any number is going to be fine except for positive and negative 7. Letter C, no division, but we do have a radical, an even indexed radical. So I'm going to take what is under the radical and set it greater than or equal to 0. I will add 27 to each side and divide by 9. x must be greater than or equal to 3. Any number less than that, and you'll get a negative under that radical. Letter D, we have a radical and we have division. And just like in the example, our radical is our entire denominator. So usually we set our denominators not equal to 0, and we set our radicals greater than or equal to 0. So here we're going to take what's under our radical and just set it to greater than 0, because we definitely want what's under the radical to be positive, but in this case, because it is our denominator, we do not want it to be or equal to 0. So subtract 24 from each side. Divide by -3, remembering to flip our inequality. X must be less than 8. Or from -infinity, comma, +8, if you want to do interval notation. See here in number 2, they want us to add, subtract, multiply, and divide the functions. Find the domain of each. Well, f of x, its domain is all real numbers. G of x is also a simple polynomial, domain all real numbers. So for letter A, when we add them, its domain will also be all real numbers. So f of x is x minus 5, and to that we're going to add the other function. And if we collect up our like terms, we're going to have an x squared plus x minus 6. And again, domain, all real numbers, from negative to positive infinity. Letter B, same functions, but now we are subtracting. So f of x minus g of x will be x minus 5 minus, don't forget this is a quantity, minus the quantity x squared minus 1. Okay, distribute the negative before we can simplify. And let's collect our like terms. Negative x squared plus x minus 4. All right, again, domain would be all real numbers. Letter C, f times g of x. And this is nice, it's just a couple binomials. We have our x minus, ooh, that's a terrible 5. X minus 5 times the quantity x squared minus 1. And we'll FOIL that out. We're going to get an x cubed minus x minus 5x squared plus 5. Again, I like to put mine in descending order of the exponents, so the cubed will go first. Minus a 5x squared minus an x plus 5. Again, domain would be all real numbers. You know, it's just a simple polynomial, no division, no radicals. Letter D, f divided by g of x. So we make a fraction with the f function on top, the g function on the bottom. And remember, here we have to worry about our domain because we do not want this denominator to equal 0. X squared minus 1 cannot equal 0. Add 1 to both sides. X squared cannot equal 1. And if we take the square root of both sides, we get positive and negative 1. X cannot equal those numbers. All right, last example here, or our last practice problem, checkpoint 3. Here are our two functions. Find each of the following. Well, the first one is the sum, f plus g of x. And that's simply we add them up, and it's radical x minus 3 plus radical x plus 1. So there's the answer to part A, the sum of the two functions. Now for part B, we want the domain. Let's see, for f of x, our domain is x minus 3 must be greater than or equal to 0, or x is greater than or equal to 3. The domain of the g of x function is radical x plus 1, and so that we take what's under the radical and set that greater than or equal to 0 and tell ourselves that x must be greater than or equal to negative 1. Again, if you want to think about it like this, we have our 3 to infinity, and we have our negative 1 to infinity. Where do those domains overlap? Or you could think, what is the more restrictive of the two? Well, that would be the 3 to infinity. So the sum, f plus g of x, its domain has to be 3 to infinity. All right, and I believe that's it for the video. There are some homework problems to go with the section. Right there on page 297-98, looks like a nice string of them there. Again, pay extra attention to those even ones. They're not in the back of the book. And I take extra attention as I'm grading your homework to those problems.